In this video we're going to go over how to calculate the resistance of a wire and also look at some real-life applications of resistivity and other aspects of DC circuits. So the resistance of a wire basically depends on two things: the type of material and the shape of the wire. So the resistance increases as the length of the wire increases, because there's basically more stuff for the electrons to move through. And since there's more stuff that they have to move through, there's more of a chance of them bumping into various things such as the metal ions, which slows the electrons down. And the resistance decreases as the cross-sectional area of the wire increases, because there's more space for the electrons to travel through. And so the length and the cross-sectional area cover the shape component of the resistance. So the type of material, that part, is covered by something called the resistivity. And the resistivity of a material characterizes how hard it is for current to flow through that material. So it has a set value for each different material. So you can look it up in a table. And so the resistivity of a material basically depends on how many free electrons per atom the material has. Because if there's more free electrons, then current can flow easily, because free electrons are what make up the current. So the equation for the resistance of a section of wire is the resistance is equal to the resistivity times the length divided by the cross-sectional area. And so for many materials, the resistivity increases with temperature, because remember, in a wire we have these positive metal ions that are stationary in an array, and then the electrons moving past them. So at higher temperatures, these metal ions are vibrating in place at greater speeds, because the temperature is increasing. So since they're vibrating faster, there's a greater chance of these electrons bumping into the metal ions, which slows the electrons down, so the resistance is increased. So there are some materials called superconductors which actually have zero resistance at very low temperatures. So as you can see here, like normal, the resistivity increases with temperature, but at a certain critical temperature, the resistivity drops all the way to zero. And so if we have a current in a superconductor, even after the potential difference drops to zero, the current will still persist in the material. And other materials called semiconductors actually have less resistivity as the temperature increases, which is opposite to a lot of materials. And so an example of a semiconductor is silicon. And basically this happens because in silicon the electrons are not free, such as in metals. So at low temperatures, the resistance of silicon is very high, because there are no free electrons to conduct the current. But as the temperature increases, some of the electrons can get loose. And so as the temperature increases, more and more electrons can get loose, and the more free electrons there are, the more current can be conducted. So that's why resistance decreases in these type of materials as the temperature increases. So far we've mainly been talking about electrons as the current, such as in a metal. But remember, current is just the movement of charged particles, not necessarily electrons. So current can also be made up of electrolytes, which are substances that have free ions. Such an example of these are sodium and chlorine ions, Na plus and Cl minus. These ions are common in our body, and they can form currents when an electric field is applied to them from the heart. The sodium and chlorine ions are also involved in transferring electrical signals through neurons throughout the body. And so a circuit breaker is something that opens a switch when the current reaches a certain value. So this stops basically overheating within the circuit. So when the current is too high, then to prevent further damage, the circuit breaker activates, and it basically makes it so the current can no longer flow. So this protects the circuit.